So good day students, and welcome back to the Scholars Universal Secondary School online physics class. So today we'll be rounding off on the topic refraction of light. So last class we concluded on additive and subtractive mixing of light and colors. So now moving today, we're talking about what? Refraction in lenses. So we're talking about refraction through lenses. So now the first thing is, what is a lens? A lens is any transparent material that has two faces, of which at least one of those two faces has to be curved. That means if you have a transparent material, note a transparent material that has two faces but has no face to be curved, that material cannot still be called what? A lens. But if you have a transparent material that has just two faces, just two, and you have at least one of them to be curved, either one is curved, the other is another shape, or both are curved, that is what's known as what? A lens. Now there are just two kinds of lenses generally, just two kinds of lenses, as they are given by the nature of their faces, the shape of their faces. Now the first one is what? Convex lens or converging lens. Now this is the type of lens that makes a parallel beam of light to converge at a point. Now this kind of lens is what? It has the center to be thicker than the edges. Now while the concave lens or the diverging lens is a lens that makes a parallel beam of light. Notice that we're always using what? Parallel beam of light. But now instead of making this to converge, it makes it what? To appear to diverge, meaning it is not actually diverging from that point, but it makes it to appear to diverge, meaning what? It is giving us an apparent image, which is what? A virtual image. So that means a convex lens is going to give us what? A real image, while the concave lens is going to give us what? A virtual image. Now this type of lens, which is a concave lens, has the edges to be thicker than the center, meaning the center is what? Thinner than the edges. So to show you what I'm talking about, you can see the first two here at the top. These are examples of what? Or the convex lenses. You can see they are thicker at the center than at the edges. These are the edges and this is the center. You can see. But for the concave lens, you have what? The center to be thinner than the edges, meaning they are thicker at edges than at the center. Now for the convex lens, like what I said, remember you can see this is the parallel beam of light converging at this point. Parallel beam of light converging at what? This point. So moving on from there, now move towards types of lenses. Now remember I said we have just two kinds of lenses, but these lenses can now be summarized, or let's say split into 6 basic types. Now for the convex lens, you have 3 types of convex lenses, and you have what? 3 types of concave lenses. Now the first one, which is A here, you can see is what's known as a biconvex lens. Now how was this gotten? Now you can see from here, this is what? A convex face, and this is another convex face, giving what? 2 convex faces. That's why it is called what? The biconvex. Now from here you can see this is what? A straight face, a straight edge, and this is what? A curved face, giving what? Plano convex. You can see this is what? This is a convex face. That's why it's called what? Plano convex, from the words plane, which is a straight line, and what? Convex side. Then the third one is what? Concave convex, given by what? Concave face, then a convex face. Now you can see these are what? Types of convex. Now let's move to types of concave. Now you can see this face here is given by what? Is a concave face, and this is also what? A concave face, giving what? 2 concave faces. That's why it is termed what? Biconcave. Now what about this? You have what? A plane face, and you have what? A concave face. You have a plane face and you have a concave face, giving us what? Plano concave. You get? Now for the final one, you have what? This is going to give us what? A convex face, while this is what? A concave face. Now this is going to be leading to what? A convexo. Note that the ones that are having are not biconcave or biconvex, the first part of that name is going to be having what? A letter O at the back. You can see plano convex, you have concavo convex, you have plano concave, and you have what? Convexo concave. Yes. So let's move on. Now we're talking about parameters of a lens. Now just like when we talked about the curved mirrors, that we talked about the parameters of curved mirrors, so now we're also talking about parameters of a lens. So we're talking about the optical center, the principal axis, the principal focus, focal length, and the power of a lens. So what's the optic center? The optic center is a point through which all rays of light passing through that point, which is the optic, that point. Any ray of light that passes through the optic center of a lens will pass through without getting deviated, meaning it's not going to change its direction. Now, what's the principal axis? The principal axis is the line that joins the optic center of the lens and the center of curvatures of both curved surfaces. Remember how to get your center of curvature. That is what you complete the sphere that is giving a face. Then the center of that sphere is giving us the center of curvature. So the line that joins the optic center of the lens with the center of curvature of each of the two curved surfaces is given as what? As the principal axis. Now, what's the principal focus? The principal focus is the point where all parallel rays that are close to the principal axis. Now note, all parallel rays, giving what? A parallel beam. But note, what you should note there precisely is what? Close to the principal axis. Close. It has to be close to the principal axis. If the rays are far from the principal axis, then you cannot use those rays to determine the principal focus. But if you have a situation where you have parallel rays and they are close to the principal axis, now if you make these rays incident on a converging lens, the rays will converge at this point, which is the principal focus. Those rays will converge at the principal focus. But if they are incident on a diverging lens, they will appear to diverge from this principal focus. So, what do you mean by focal length? Now, the focal length is just simple: the distance between where the point which is known as a principal focus and the optic center. The focal length is just the distance between the optic center and the principal focus. Now, moving to the last one, which is power of lens. Now, power of lens is just basically the reciprocal of focal length. Remember, your focal length is a distance. It needs to be given in either maybe units of distance, which is meter, centimeter, millimeters. But note that the power of lens can only be gotten if the focal length is in meters. So if you are given the focal length, if you measure the focal length in centimeters or millimeters or decimeters, you have to convert that focal length you've gotten back to meters before you can use to calculate the power of lens. So, for example, if I have my focal length of a lens as 20 centimeters, I have to first convert that 20 centimeters to meters to give 0.2 meters. And after doing that, to get my power of lens, I now find the reciprocal of 0.2, which is 1 over 0.2, to give me 5 diopters. So diopters is the unit for power of lens, and it's denoted by the capital letter D. So moving on, you can see these are the examples of the lenses. You can see the first two here are the converging lenses, converging, while this is a diverging lens. Now you can see this is the optical center, that is the center of the lens. Then you have the principal axis here. Then the principal focus is at this point where the parallel rays converge for a converging lens, and you can see the principal focus is here where the rays appear to diverge. You can see the rays are going in this direction, but they appear to diverge from this point. Then your focal length is distance between the optic center and the principal focus. So let's move on to construction of ray diagrams. Now, how do you construct ray diagrams for lenses? Now, the first thing is you have just two methods which are mostly used. Now, the third one is just used in some cases. Now, the first thing is, now a ray from the object that is parallel to the principal axis will get refracted and then appear at the principal focus. Now, if you have a ray of light that is parallel to the principal axis, like take this as an example, you have a ray of light that is parallel to the principal axis, will get refracted and then pass through the principal focus. Then for the second one, you have a ray from the object passing through the optical center will pass through the lens undeviated. Now remember, I said the optical center is the point on the lens where all rays that pass through do not get deviated. So looking at this now, this is the optic center. So if you have a ray that passes through this optical center, it will not gets deviated. So now the point of intersection of these two rays that you've gotten is what gives you where the object is formed. Okay, but in some cases you might need a third ray. Now this third ray is given by a ray from the object that passes through the principal focus will emerge as parallel to the principal axis. So this is just from the principle of reversibility of light from the first one. The first one says that a ray from the object that passes through that is parallel to the principal axis will get refracted and pass through the principal focus. So just from the principle of reversibility of light, this is just giving that a ray that is now coming from the principal focus and passes to the lens will get parallel to the principal axis. So these are the images formed by a convex lens. You can see the object distances and the final image here. This is talking about parallel rays coming from infinity all those rays will get converged at what, at the focal point. So you have your image here. Now this is when your object is what, is at a distance that is greater than the center of curvature, which is what, 2f. So you have your image formed between what, f and 2f. This is just similar distances or similar images formed by what, the concave mirror. So you can see that after you draw the ray diagrams for images formed by a convex lens, they will look exactly or very similar to what, to the images formed by what, the concave mirror. Remember, the concave mirror is a what, is a converging mirror, and the convex lens is a what, is a converging lens. So they both perform the same duties. They both converge rays. That is why they have similar what, images formed. Now remember, when you are drawing your ray diagrams, also you are using your ray diagrams to calculate, also determine is what, the properties of the image, which we have used the acronym for in our subsequent classes, or previous classes rather, as what, LOST, which is what, location, orientation, size, and type. So you can check through these ray diagrams to see and ensure that they are the same thing with that of what, the concave mirror. Now, so these are the images you will get. Now when your object is coming from infinity, you have your image at the focal length, and it's going to be real and inverted and diminished. So you can skim through the other object distances and image distances and their nature from here. So this is the only type of image that can be formed by a diverging lens. Remember when I talked about the diverging mirror also, the same thing happened. You only have one type of image formed by a diverging mirror. So the same thing is applicable for a lens. You only have one type of image formed by what, the diverging lens, which is this. So moving on, we also have sign convention for lens, but it's slightly different from that of what, of mirrors. So you also have two types, real is positive and new Cartesian. So for a real is positive, you have real objects and real images are considered to be at a positive distance from the mirror. Sorry, the mirror here means what, the lens. Now real objects and real images are considered to be at a positive distance from the lens. Now virtual images are at a negative distance to the lens. Now the focal length of a convex lens is always what, positive. Note, focal length of a convex lens is always positive, and the focal length of concave lens is always what, negative. So this lens formula is also given by what, 1 over v plus 1 over u equals 1 over f. Now going to magnification of images, your magnification, just as in mirrors, is just what, the image height or the image size over the object size. So you can be given as what, image height over object height, or the distance of image from the lens as what, the image distance over the object distance. And remember, our image distance is denoted by the letter v, and our object distance is denoted by the what, the letter u, giving our magnification as what, m equals v over u. So now experiments to determine the focal length of lenses. So we just use convex lens generally. So the first one is a quick but approximate method. So just like the same thing for the mirror, what you just do is what, you try to make you have a screen. You can see the screen being held by the boy here. So you try to make the rays from a distant object to what, to converge on this screen, to show on this screen. So you have your converging lens. Now you move your lens and the screen to and fro until you have what, a sharp image of the parallel of a distant object rather formed on the screen. Now after doing that, you can now calculate the distance of the lens from the screen, and that will give us what, the focal length. So you can also use mirrors to calculate the focal length of a converging lens. Now you can see from here, you have what, you have a plane mirror here, you have your convex lens, and you have an electric lamp. Now this is a screen, this is the screen you are using. Now you place a cross wire here, cross wires here. Now this is the point where you place the original cross wires, remember. Now after the rays from this, remember you are trying to calculate the focal length to be given as what, this. Now when the rays from this get parallel after being refracted by the what, by the convex lens, and they hit the plane mirror, remember the magnification of a plane mirror is what, 1. So it is going to be what, reflected by the plane mirror in that same direction, and it's going to what, pass through the convex lens again, and what, then get refracted and is impinged back on this screen. Now the same thing happens to the other ray that is coming in this direction. Now the point where you now have the image formed, so what you do is you have your lamp here, you move your convex lens from the screen. You don't move the screen is placed constant. So when you move your convex lens and you now have the sharp image also formed back on this screen, Then you measure the distance between the convex lens and the screen to get your the focal length. So you can also use the lens formula. So what you just do is you place a convex lens in front of an illuminated object. You can see this is the illuminated object from the ray box. You can see the light here, light source, and this is the object. Now, after this, the rays from this object get refracted through this convex lens. They are going to be impinged to form an image on this screen. Now, after you get your sharp, note that, remember I said the point you pick your screen or where you calculate your distance from is where you have a sharp and the brightest image. Now when you have the sharpest image, calculate the distance between the object and the lens to give the object distance, and calculate the distance between the lens and the screen to give the image distance. Now after doing that, you come to your table of values. You have your u, because you put in your values of your object distance against the values of your image distances. And after doing that, you look for the reciprocal of both, and then you plot your graph. Now the points, you plot your graph of 1 over v against 1 over u. Now the points of intersection of the graph with the axis is going to give you the reciprocal of the focal length. So you can see from here where your 1 over v is plotted against 1 over u. Now at this point where the graph intersects the y-axis, calculate the distance from here to your origin. Now that distance is going to give you the power of that length, which is 1 over focal length. So to get your focal length, you have to now reciprocate that distance. So likewise, when you look at the 1 over u axis, the same thing happens. So that should be the end of the class on refraction of light. So you'll be getting your assignments, your final assignments for the week sent to you via the online platform.